moving on. Right, so B12 now. This is one where it's drawing resonance structure. So I'm not going to do most of them. Right, so the one that I guess I didn't have PO4 here. Right, but if you're drawing resonance structures, right, you can just simply move around things. So I'm going to do the ClO4 minus because I didn't do that one earlier because that was part of B4 as well. But if we do, if we draw out the Lewis structure for ClO4 minus, right, we have chlorine, so it has 7 electrons around it. 1, 2, 3, 4, 5, 6, 7. We have 4 oxygens, so 1, 2, 3, 4, 5, 6. Excuse me. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We have one extra electron, right? So I'm going to put that on one of the peripheral atoms in the most electronegative one. And so, right, there's 4 of them. I'm just going to put it on this one right here because it's going to make my life slightly easier. Right, because now looking at it, right, there's one unpaired electron on that oxygen that has a formal negative charge, right? And then the chlorine has that one unpaired electron. And so those two can combine together, right? Join forces and form a single, let me move my picture. Yeah, good enough. Right, to form a single sigma bond, right? So now the question becomes, well, what happens with all of the other oxygens? And so my first approach is I know that each one of those oxygens needs 2 electrons to get to a full octet. And I know that I have 3 lone pairs, right, filled with 2 electrons apiece on that chlorine. So I can redraw and rearrange those oxygens. So that way, essentially, I'm making 3 lone pairs on each one of those oxygens right off the bat right there, and have like an empty orbital, so to say, that now these lone pairs can directly bind into, right? So you can bind directly into them right there like that. And so going through, right, I didn't add any electrons. I didn't take any out, right? There's still same number of electrons as before. And so what I have is 1, 2, 3, 4, 5, 6, 7, 8 around those oxygens, right? I have 7 electrons directly around the oxygen. So each one of those has a negative formal charge. Looking at the chlorine, right? Right, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around that chlorine. So it meets the octet rule. So we're set there. And going through, right, it had started off with 7 electrons. Now it only has 4. So it has a formal charge of 3 plus, right? And going through and adding up all the charges, what we get is an overall charge of -1, which is what we have for the formula in that case, right? So that right there is, our Lewis structure in this case. And so now what we can do is we can start drawing resonance structures, right? And there's a few different ones that you can do. I'm just going to do like the most significant ones in terms of like changing how many formal charges we have overall, right? One thing you can do once you have one of them, you can start moving around the double bonds that form and start looking at how that all affects things, right? Because technically, even though you're moving a double bond and everything is symmetric, you could technically do a isotopic labeling experiment, right, where one of them is oxygen 16, right, the most common isotope, and another one becomes oxygen 18, and that slightly changes what's going on, right? So they're not, so even though they're symmetrically equivalent, in actuality, right, they're different atoms. And so 2 different resonance structures, even though you're just moving it between 2 different things, are still different, right? They're still different resonance structures in those cases. So right, but if I go through, so what I can do, in terms of doing resonance structures, this is going to be a very common way once you guys get into orgo in terms of how to approach it. But one thing you can do is you can just simply, move lone pairs into forming bonds, or you can move bonds and move them into forming lone pairs, and the way that that's always drawn in orgo, and I'm just going to show that right here because it just makes my life easier in terms of how I approach it, is you always start off at where that electron pair is, and then the arrow should end up where you're putting that electron pair. So in this case right here, I'm just going to go with this guy. I'm saying I have this, lone pair of electrons in this oxygen, and I'm going to say, okay, wait, I'm going to put that into that chlorine oxygen bond right there to form a double bond now. And so what you get is a double bond between these 2 guys right here. Draw everything else the same as before. right? So we have that right there, right? So now those, I didn't change how many electrons I have overall. All I did was take 2 electrons that were in a lone pair and I made them be a double bond between the chlorine and the oxygen. And so if I go through now, right, and I count up all the different formal charges on the 2 atoms that I changed, right? I have 1, 2, 3, 4, 5, 6 electrons directly around that oxygen. I have 8 electrons total, right? Because there's 2 more within those bonds. So that's a full octet. But because it has 6, it starts off with 6, right? Is what neutral oxygen is, right? That has a formal charge of 0, right? It doesn't have a formal charge. Looking at the chlorine, right now, what we have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons total around it, right? So now we're in the extended octet territory, which is fine. Chlorine's in the 3rd row, so we don't have to worry about that. But if we start adding up the formal charges, right, what we have now is 1, 2, 3, 4, 5 electrons directly around it. Right, so if we have 5, it started off, with 7, right? That's what chlorine is. What we get then is a formal charge of 2 plus now for that chlorine. Excuse me. So we have that, and so the next thing that we can do is we can, work our way through and see, can we do that with any more of these systems? And so if we do that, what we can do is we can take now this lone pair right here, right? And we can put that into that double bond. And so the way that now looks is like this right here. Right? So going through, right, now that that oxygen has a double bond to it, right, it only has 6 electrons around it, but it still has a full octet. And so, it's going to be a neutral formal charge, right, formal charge of 0. Now the chlorine, right, looking at that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons directly around it, right? So that is then, fine, extended octet. But then in terms of thinking about the formal charge, right, we have 1, 2, 3, 4, 5, 6, right? So it has 6 electrons. It wants to have 7, right, to be neutral, so it's going to have a 1 plus charge. And so again, right, like also going back, thinking about it, right, overall the charge should be -1, right? If we add up all the charges for each one of these resonance structures, it's going to give us something that is -1 overall, right? So, 2 negative charges, 1 positive charge, still 1 negative charge. We do another resonance structure, right? We can move this lone pair into here, right? And so now what we have is this structure right here, which is probably where a lot of you maybe even started off on your own, thinking about how to approach it, right? When you were thinking like, okay, right, chlorine can do an extended octet. We're going to get to this point because if we're looking at it, right, those 3 oxygens with the double bonds, they all have 8 electrons, right, filled within their orbital. They have 6, right, directly around it, so to say. And so what you get is a formal charge of 0 for each one of them. And now if we look at the chlorine, right, what we have is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons, right? So extended octet, perfectly fine. It has 1, 2, 3, 4, 5, 6, 7 electrons, right, directly there in the structure there that I drew. And so, right, so it starts off with 7. It has 7 now, so it has a formal charge of 0. Right, and then overall, right, we only have 1 negative charge, right, and that's from that oxygen that has the extra electron in it, right, and so we have this structure right here, and so right, so those are going to be your 4 basic resonance structures that you would have, right. Each one of them is valid, right. All of them work, right. They're all different. You can then go, and make different ones where you're like, oh, I'm going to move the lone pair, or sorry, the double bond from, the oxygen that's on the right, and I'm going to move that one to the one that's all the way up top, and blah, blah, blah. Those are all perfectly fine. Those are all resonance structures as well, right? But they're just not, that unique, but they're still, different. This is a point that I want to clarify. There's probably somebody out there who's like, oh, you can actually just go in one more resonance structure, right? So one thing you can do is take this guy, right? And you can be like, oh, well, I'm going to put this into here, right? And then you can draw that resonance structure. And so that's just simply then all double bonds all around. Right, in this case. And so now what you have then is the formal negative charge on the chlorine. All of let me move my face. Oh no. Oh, I grabbed the wrong thing. Let's move this back. There we go. Centered. Webcam. Move. Right. So you could always draw that right there. However, I will say it is extremely unlikely, right? Where you suddenly have, and I don't know, how Professor Rubenstein really would take that. If you're suddenly going from something that's going like from a whole bunch of positive charges to simply jumping to something that's negative, especially considering that that negative charge now is on the least electronegative atom that's part of that molecule. Right. So out of all the atoms there, right, it's the least electronegative one. So least likely, but technically, right, it's a valid one because in terms of extended octets and octets, right, everything matches, the overall charge matches. Formal charges add up the way that you're supposed to. So that's just a thing to keep in mind. Cool. Let me just move this right there. So that's all I'm